First speaker is Joshua Mundinger, and we'll talk about quantization of restricted Lagrangian subvarieties in positive characteristic.
I'd like to thank the organizers for the invitation to speak. So let's begin. A will be a field, and X will be a smooth algebraic variety over K. And we're going to assume that it has a symplectic form. So maybe an algebraic symplectic form. And we know this gives X the structure of a Poisson variety. So in this talk, we're going to deal with formal deformation quantization of the symplectic variety X. So a formal quantization of X is a sheaf OH, which depends on some parameter H. Since this is formal, that means that we're algebras over the ring of power series in H. And it's flat and complete over the power series ring. And this ring is supposed to be a non-commutative ring, which recovers the structure sheaf when you set H equal to 0. So it's commutative at H equals 0, but the first order deviation from non-commutativity is controlled by the Poisson bracket. In particular, if I have the commutator of two elements, well, it's 0 mod H, and the first order difference is the Poisson bracket. So the commutator is equivalent to the Poisson bracket to first order. So locally, this thing is going to look like a star product, but maybe globally, you can't split this quotient map. Okay, so now we dive into positive characteristic. So let's assume that K is a positive characteristic, and I assume that it's bigger than 2 because we like to divide by 2. So one reason why you would want to do this in the first place is that this quantization often has large centers. And this is very useful for understanding associated modules and eventually representation theory. So for example, let's take X to be the cotangent bundle of some smooth variety. Then a quantization is essentially given by differential operators on Z and by differential operators here, I mean the ring generated over power series and functions on Z by the tangent sheaf modulo the relations, the commutator of 2, well, I should say, in the ring, the commutator is equal to H bar times the commutator of vector fields. And if I try to commute a vector field past a function, this is equal to H times the derivative of that function along the vector field. So the H's are here so that this is indeed a quantization. So my claim is that the ring of differential operators actually has a very large center in positive characteristic. So here are two ways to construct central elements. So if I have a function on Z, then its pth power is in the center. And this is just the fact that if I take the derivative of the pth power of something, by the Leibniz rule, this is p times f times p minus 1, derivative of f, and p is 0. So derivatives of pth powers are 0. So the pth power of a function lies in the center. So this is already pretty big, but in fact, there's a contribution to the center coming from vector fields. And this has to do with this classical observation. If I have a vector field, then in fact, its pth power, thought of as an operator on functions, is also a vector field. This is something you can check just with the Leibniz rule. If theta satisfies the Leibniz rule, then its pth power also does in characteristic p. Now, inside this ring of differential operators, there are two different ways of taking the pth power. I can take the pth power with respect to the product in this ring, or I could take the pth power as an operator, which in fact lies in the tangent bundle. So it's in degree 1 in this algebra. And if I put h in the appropriate places, then it turns out that this operator is in the center also.
You embed the vector field multiplication by h. The company about multiplication by h.
Yes, yes. So for every function, its pth power is central. For every vector field, this sort of twisted pth power is central. So in fact, the whole algebra is finite over its center. So this is very useful. So Professor Kovnikov and Gladen described quantizations that have a similar property in characteristic P. So a quantization OH is called Frobenius split if there exists a ring map, S for splitting, which goes from pth powers of functions, so this is a commutative ring, into my non-commutative ring, such that first, the image of S is central, and, well, it's supposed to look like the Frobenius. So if I take S on a pth power, then this is equivalent to taking the pth power of some lift of F mod h to the p minus 1. So same h to the p minus 1 is over here. So in the case of differential operators, this S involves the pth power vector fields. That's the first order derivation from being just literally the pth power in the ring of differential operators. So in general, if you have a Frobenius split quantization, then it makes sense to ask sort of what goes here. What's the difference between taking the honest pth power and this central splitting map? So if I have some section of my Frobenius split quantization, it makes sense to take, I'll call it x bracket p, which is the difference between the pth power and the splitting applied to x to the p. Here, maybe this is x mod h. And then I divide by h to the p minus 1, and I take this mod h. So this is an element of OX, and you can show that this actually descends to OX. And this is generalizing this p to the power of vector fields. So let me tell you some properties of this. So the first property, if I have a scalar, maybe I should say this descends to a map from OX to OX. And I'll tell you now the properties of this map. If I take this bracket p to the power of lambda times x, this is lambda to the p, x bracket p. 2, this now actually is not additive because this term here is not an additive function if I take the p to the power of something in a non-commutative ring. However, the failure to be additive is nice. So the difference between x plus y to the bracket p and x to the bracket p plus y to the bracket p is some universal polynomial in the Poisson bracket, which is originally due to Jacobson, who gave some formula. And the third property is that if you take the Poisson bracket with x bracket p, this is the same as taking the Poisson bracket with x p times. So properties 1, 2, 3 make OX with the Poisson bracket into what's called a restricted Lie algebra. A restricted Lie algebra is exactly a Lie algebra with a p to the power map satisfying these 3 properties. And Bezrikov-Nikov and Clayton's main theorem well, there are sort of 2 parts to it, to their work. So first, they classified when a symplectic variety admits a restricted structure. So by restricted structure, in particular, we'll have that the Poisson bracket is in fact a restricted Lie algebra satisfying these properties. And there's some compatibility with multiplication, which I won't say. And B, if X is restricted and we impose some cohomology vanishing condition, namely H2 of the structure sheaf is 0, then Frobenius split quantizations exist. Okay, so this is about formal deformation quantization positive characteristic. So now we can come to the part of the title which is about restricted Lagrangian subvarieties. So one question is the following. If I start with some OX module, when can I quantize it to some module over the non-commutative ring such that I recover my original module when I go to H equals 0? In the original works of Bezrikov-Nikov and co-authors, these modules over the non-commutative ring that they construct are what they use as tilting bundles on X or varieties associated to X in order to construct various derived equivalences in geometric representation theory. So construction of these modules is interesting. Gauber has a theorem that in this situation, the support of F has to be coisotropic. So maybe the simplest but already interesting situation is if the support of F is Lagrangian and F is actually a line bundle on this Lagrangian. So since we're in positive characteristic, OH has this large center. This splitting map tells you that there's a map in from Heath powers of functions. And in fact, if you take power series and such, then the isomorphism is parameterized. The center is parameterized by these power series of Heath powers. So you could ask for the support of one of these quantizations in the center of your non-commutative ring. And this should really be considered as given data for this problem. So instead of just asking, starting with some sheaf on, or the push forward of a line bundle on your Lagrangian, you can also ask, what is the support going to be in the center? And then try to construct a module with not only the correct reduction mod H, but also the correct support. So it's not too hard to see that the support will be some formal deformation of Y, or sorry, of the support of F. So we'll ask that the support for today, the support in the center is essentially functions on the support of F. The ideal of the support of F, and then extend by power series. So there's no formal deformation at all for today, but treating a more general case is possible. Okay. So this condition actually forces some compatibility of Y with this restricted structure. So let me say Y is Lagrangian. So a Lagrangian is restricted if the ideal sheaf of Y is closed under this restricted operation, this bracket P. So recall that because Y is coisotropic, this implies that the Poisson bracket of two functions in the ideal of Y, again, is in the ideal of Y. So the ideal of Y is a Lie algebra under the Poisson bracket, and Y is restricted if the ideal is a restricted Lie algebra. So the quantization problem, as I've set it up, actually only has a solution when Y is restricted because of this support condition. But using this, we can, in fact, solve the quantization problem. And the first step is a kind of tubular neighborhood theorem. So as Pavel was discussing in the last talk, there's the famous tubular neighborhood theorem for smooth Lagrangians, but in the algebraic or holomorphic setting, there may be some global obstruction to the existence of a tubular neighborhood. But in fact, locally holomorphically, there will be a tubular neighborhood of a Lagrangian subvariety. So the theorem here is some analog in this positive characteristic setting in case that we have a restricted Lagrangian subvariety. So here's the statement. I forgot. I have to tell you one more thing. So there are all these p powers floating around. And we sort of have to work locally on the ring of p powers. So there's a standard convention on how to deal with this. So the Frobenius twist z prime of z, z is a variety, is the pullback of the following diagram. Where here we have the Frobenius of k, and the Frobenius of z induces a map here, which is called the relative Frobenius. So if z was the polynomial ring on n variables, I should say spec, then z prime is spec of the polynomial ring in the p powers. On the level of functions, you've taken p powers, but you take the k algebra generated by p powers. Okay, now we can state the tubular neighborhood theorem. So we have a restricted Lagrangian. Then locally, that is with respect to some cover on y prime. So the scheme defined by p powers of functions on y, the inclusion of y into x, and y as the zero section of the cotangent bundle on y. If we pass to this cover, are actually isomorphic. And here the isomorphism is of restricted symplectic structures. So we remember symplectic form and this p power operation. Now I have to tell you what kind of cover is this. This is actually an FPQC cover. So maybe a little technical, but in the course of the proof, you might have to extract a pth root of a function on y prime. And FPQC covers let you do that. But this is really good enough to solve the original question. So to solve the quantization of some line bundle on y, first quantize the zero section. So essentially on the cotangent bundle, you can show after maybe passing to some further cover, your quantization will look like differential operators. And so this is just some differential geometry involving connections. And then once you've done this, you try to glue using the tubular neighborhood theorem. So I think I'm out of time, so I won't give a formal statement on the conclusion of gluing, but the theorem turns out to be that there is some cohomology class, which turns out to live in the Brouwer group of Y, which vanishes if and only if there exists a quantization of some line bundle on Y. Okay, thank you.
Is there a classification of when these Frobenius quantizations are mild?
Yes. So in fact, they're always Azamaya algebras. If you invert H. So at H equals 0, it's commutative, so it can't be, but. Yes.
Would it be possible to ask the question again?
Yeah, no, I was asking when are these quantizations Azamaya algebras? The
Yes.
answer was always.
Once you invert H.
There's some really interesting results downstream of what Bezrakhovnikov and Clayton did. Do you have some applications in mind kind of connected with that?
Yes, although very preliminarily. So right. So one of the applications is this symplectic Mackay correspondence. So I think there's some hope to use positive characteristic methods to study related problems like n factorial theorem. But I mean, then the Lagrangian correspondences involved are singular, so there's more difficulties. Here, everything was smooth.
Is there any relation with quantum groups at roots of unity?
So
It's just
The-
similar structure.
right, so the quantum groups at root of unity, I think, are also Azamaya over their center. As far as the results I talked about today, these quantization problems, I'm not sure, but there are many sort of structural similarities between these Azamaya algebras and positive characteristic and these sort of quantum at a root of unity situation.
Thank you.
General question.